Alright, dear students, good morning. We will continue with this thermodynamics, and I hope you have already read the notes that I sent to you last time. So just to continue with this, let me just make some reminder again. We have already seen some process earlier, like isochoric process. And this isochoric process, this is a thermodynamic process that takes place at constant volume. So your volume is constant. Then next we have isobaric process, where this pressure is equal to constant, and you have this adiabatic process that takes place when there is no exchange of heat between the system and the surrounding. So you can write no exchange of heat between the system is but a gas and surrounding. And you have isothermal process, and this one takes place at constant temperature. So these are the important terms that you need to memorize. So in today's class, we'll see this work done during the expansion of a gas. Okay. Imagine here is a gas. Here is the piston, and the piston is expanded from A to another point here, B. So during expansion of the gas should be having two volume. V1 is the initial volume, and V2 is going to be the final volume here. And this final volume should be greater than initial volume. So before you actually talk about the expansion from A to B, from V1 to V2, let us imagine that the gas is expanded through a small distance of dx here. Just through a small distance dx. So in this case, the work done should be small. So small work done during expansion through dx will be given by dw is equal to Fn dx. Imagine this is your cylinder, and this is the piston having area of A, and this piston is going to move through a small distance dx. So in this case, the work done is given by F dx here. So here, pressure is equal to force by area. So this will give you force is equal to P and A. So I put here, therefore your work done is equal to PA dx here. But if you look at the figure, this A and dx, it gives this product, it gives volume of the cylinder here. So the volume is small volume, so I can write dV. So this A dx I can write as dV. So therefore your work done becomes P dV here. This is your equation number 1. So equation number 1 simply represents the small work done during expansion of the gas through dx only here. But our aim is to expand the gas from A to B, from volume B1 to volume B2 here. So this equation number 1 should be integrated. So once you do integration on both sides, you should get integration of dw is equal to w, we know it. So on the left hand side, if you do the integration, you are going to get only w, and on the right hand side you have p dv. But on the right hand side there is volume, so volume is expanding from v1 to v2. You have to write like this. So this is the general equation for work done during expansion of a gas. And this equation you can apply to isothermal process. At the same time, another one is adiabatic process. You can apply it. So in the next, we will see how do we apply this work done equation. Work is equal to integration of P dV from V1 to V2 to isothermal process. So our topic should be work done during isothermal expansion of a gas. Work done during isothermal expansion of a gas. This will be our topic. Just now we have seen that work is equal to integration of P dV from V1 to V2, and from equation of stat PV is equal to RT. Actually this formula, equation of stat, it should be found in your chemistry, or class 11 chemistry. If you have not seen it before, just imagine like this: PV is equal to RT. This ideal gas equation, or the equation of stat, it simply connects pressure, volume and temperature of a gas, where R is a constant, and this constant is known as constant of gas, a gas constant here. Okay, PV is equal to RT, as I said again. P for the pressure, V for the volume, P for the pressure, V for the volume of the gas, and this T for temperature, and R is the gas constant. So the equation that connects pressure, volume and temperature of a gas, that is what we call as the equation of stat. So otherwise I trouble to shoot on this camera. Okay, then we are talking about isothermal process. So during isothermal process, temperature is going to be constant. So you put temperature constant here. Therefore your PV is equal to a constant. Why? Because R is constant, T is constant. So these two terms I take it as constant. And note that K is equal to RT. So from here I put P is equal to K by V here in this equation. So you have this work is equal to K by V dV from V1 to V2. Then you take K outside integration, you have 1 by V dV from V1 to V2, and you have to know that integration of 1 by X dx, this is equal to log of X. So if you apply the same formula, you can write K log of V from V1 to V2 here. So this is equal to K log of, instead of V you write the upper limit, it becomes V2 followed by minus, instead of V write on this log of V1 here. So which is equal to K is already equal to RT, and this one is similar to log A minus log B, log A minus log B, which is equal to log of A by B. So using this you can write as log of V2 by V1. This is the equation. And another reminder is that this work done equals equation RT log of V2 by V1. In this equation, this log of E, this is equal to 2.303 log of 10 here. This is the relation between natural logarithm and the general logarithm here. So you can put this work done as RT instead of this log E. You can write 2.303 log of 10 V2 by V1. So this is the final equation that represents work done during isothermal process. This is the work done during isothermal process. Okay, next we need to see a very important diagram. That is what we call as the indicator diagram. So here is the indicator diagram. Okay, in this indicator diagram, let's see what do we do. We are going to plot a graph between pressure and volume here. So this is the axis for pressure and this is the axis for volume here. Now what happened is, suppose a gas is expanding right now. During expansion of a gas, volume is increasing. So I'll just take 2 points here and B. There's an A here with the value of P1, V1. Let us say this is V1 and this one is, say, P1 here. And another point B with values of P2 and V2 here. Here. So this is going to be V2, it's going to be P2 here. Then what happens is, when a gas is expanded, volume goes on increasing, pressure is decreasing. Just imagine the situation. During expansion of a gas, volume should be increasing and pressure should be decreasing here. Okay? So I can plot it here with a curve here, like this. So if you choose these 2 points here A and B, compare the volume. Volume is very large. Volume is increasing. Volume is increasing from V1 to V2. Volume increasing, but pressure is decreasing from P1 to P2 here. It means if volume increases, pressure decreases, means this is expansion here. So this is going to be expansion of the gas. Similarly, if you take another graph here, so this is P, this is V here. The opposite way I take it here, AB here with the same coordinates P2, V2. Another B here, P1, V1 here. Suppose this will be your V2. This will be your P2 again. And here, this should be P1. This should be V1 again. Then, say during compression of the gas, imagine there is compression. During compression, suppose if you move it from A to B, for example, volume is decreasing. Volume decreases from V2 to V1, but pressure is rising from P2 to P1 here. Volume is decreasing. Now you can see volume is decreasing. Just choose these 2 points. At A, volume is very large, pressure is low. At B, pressure is high, volume is low. So it means there is compression. So this is the indicator diagram for compression of a gas and expansion of a gas, and you just try to revise this 2 graphs. This is very important. So for today's assignment, that is your assignment. You send me the answers of these questions. That is by 10 p.m. today. That is 30th. 30th is the last day. The first question is, explain. Number 1, isothermal process. Number 2, adiabatic process. Number 3, isobaric process. Explain these 3. And this one, derive the expression for work done during isothermal expansion of a gas. So try to send the answer to me, that is by 10 p.m. and I will check how many of you are responding to my classes. Okay then, we'll stop for today here.